Alright guys, we're going to go on to example 5 now. Really quickly, before I actually go on to example 5, I want to talk about the fact that a critical point doesn't necessarily always yield a min or a max. So take a function that looks like this. So in this case, the function would have a derivative that's equal to 0 at that point, but it's not a min or a max, because on one side the value is decreasing and on the other side the value is increasing. So it's not a min or a max. So the first derivative test can give us critical points, but we have to use other methods to verify that that critical point is a min or a max. Another example would be a function that looks like this. So in this case, the function, the derivative would be undefined. And so the first derivative test suggests that we have critical points when the derivative is undefined. But again, in this case, we don't have a min or a max because the function is increasing and decreasing on one side or the other. So the moral of the story is you can use the first derivative test to find your critical points, but you need to use another method to determine if the critical point is a max or a min, or in some cases neither. You can graph it, you can plug in values into the original function, or you can look at the slope like we did in the previous example. Alright, so example 5 says find the extreme values of the function f of x find the extreme values of the function f of x, and the function is given to us piecewise. In this case, we're not given the domain of the function, we're not given an interval to look on, we're just asked to find all the extreme values. So the interval that we'll look on is the domain of the function. And in this case, the domain of the function is all real numbers. So we weren't given a set interval to look in. So we're going to look in just the domain of the function. And because the domain of the function doesn't have an inclusive endpoint, all of our critical points are going to happen on the inside of the interval, and we'll be able to spot them using the first derivative test. As long as x is less than 1, the derivative of the function is negative 4x. We're just taking the derivative of the top expression and the piecewise expression. As long as the function is greater than 1, the derivative of the function is 1. Because these two slopes do not match, at x equals 1, which is where the two piecewise functions come together, the slope on one side is negative 4, and that doesn't match the slope on the other side. And so in that case, we could take some time, they do it in your book, we could take some time to do the left-handed and the right-handed limit for a more rigorous proof of this, but the slopes don't match, and so the function's derivative is undefined at x equals 1. And this is a cusp because we have a curve intersecting a line. So we're going to have something like this, a curve and then a line, and so that's a cusp. A corner is only when you have two lines joining that have different slopes. A cusp is any combination of curves. So there we go. So we're going to have a cusp So that means that actually our critical points, if we look, the only time the function is, the derivative is 0 in the top expression is when x is equal to 0. And that does happen when x is less than 1. That's important to us because we only want to be finding critical points when the piecewise function is using that expression. The other function actually doesn't ever have a critical point. It's never equal to 0, and it's never undefined. So the critical points we're going to worry about are x equals 0 and x equals 1. In order to determine whether these are max or mins, we're going to need to look at their value. So we can see f of 0. Now we're going to evaluate that using the top function because 0 is less than 1. So we're going to have 5 minus 2, 0 squared. It's going to be equal to 5. And f of 1, we're also going to be using that function. And this function is continuous, so it doesn't matter which function we use, but the way it's defined, we'll use this one, and that comes out to 3. In order to determine whether or not these are maxes or mins, we can look at what's going on either side of the function. But in this case, this is a critical point, and it's 5. And if we were to look at what the function is doing off to the left or to the right, this is an upside down parabola. And so part of our function here is an upside down parabola, and the critical point we found is the top of that parabola. So that's probably our max. And we could plug in points for the function and confirm that. At x equals 1, we have a cusp. It's the joining of the two functions. So we're going to have the left-hand side of the parabola, or sorry, the right-hand side of the parabola, and then we're going to have a line with a positive slope, x plus 2. So it's going to go up like that. So it looks like this is our minimum. And these are going to be local since we don't have an absolute largest or smallest value. This function is defined over an infinite domain, and if we graph it, we'll see the function looks like this. And so there isn't any place where we can say there isn't a value larger or smaller than these two. Actually, it goes on infinitely negative and infinitely positive. So this is a local max, and this is our local min. The function asks for us to find the extreme values. So what we would provide is that the extreme values are 5 and 3. A local max of 5 and a local min of 3.